So today we're going to talk about homomorphisms, and this is a continued conversation from what we talked about last time. So to remind ourselves, let's suppose we had a group G with an operation dot and another group G prime with an operation star. When we say phi, which is a function from G to G prime, is a homomorphism, if it preserves the group operation and the group operation is compatible with the function phi. So phi takes stuff in G and outputs things in G prime, provided that phi of the product of two elements in G is the product of the outputs 5x and 5y in the group G prime. Okay, so we gave lots of examples of different homomorphisms last class, so today we're going to talk about some more general properties of these things. Okay, so the first thing we're going to do is establish some of the sort of fundamental properties of homomorphisms from an arithmetic point of view. So suppose you had a homomorphism that took elements in G and had outputs in G prime. Then we can prove a few things. So first of all, the identity in G will get mapped to the identity in G prime. Now you notice these weird symbols EG and EG prime here. The reason that we have them written like this is because we can't use E generally because these groups are different and they have different identities. So this here is the identity in G, and this is the identity in G prime. Now, it's kind of a weird thing to actually establish this, but the only thing you have to work with the group homomorphism is the multiplicative property. So you have to use it somehow. And since the only element we have to work with here is the identity, it makes sense to use it with the identity in itself. So we observe that we can look at phi of the identity element dot itself. Now on the one hand, the identity times itself is the identity, so this should be phi of the identity element. On the other hand, this should be the product of phi of the identity element and itself because phi is a homomorphism. So we have this equality that phi of E of G times phi of E of G is phi of E of G itself. Now here when we say times, we actually mean star. Should be careful of that. Okay, so now this element here, phi of E of G, is an element in the group G prime. So it has an inverse. And so we can multiply by that inverse on the right to get phi of E of G equals the identity in G prime. Because when we multiply by phi of G, E of G inverse, it'll get rid of this on the right and it'll make the identity in the group we're dealing with, which is G prime here. Okay, phi of the inverse of an element, phi of the inverse of an element is the inverse of that phi. To see why, let's underline the things we're looking at here. We're looking at the inverse of phi of G, and we're trying to prove that that inverse is this thing. So we need to look at the product of phi of G and phi of G inverse. By the multiplicative property, that is phi of GG inverse, which is phi of the identity in G, and we just proved that's the identity in G prime. So indeed, we do have that phi of G times phi of G inverse is the identity in G prime, and you can make a similar argument to show that phi of G inverse phi of G is also the identity in G prime. And so you get that the inverse of phi of G actually is phi of G inverse. Now you can imagine if you apply this to a triple of things, that you would get that phi of the product of three things is the product on the right group of the phi of the three things. And so we get in general that phi of a product of n things is the product of the n phi's. In other words, phi of g1 through gn is phi of g1 times phi of g2 up to phi of gn. And you can actually prove this by induction. So I'll say try it inductively, but you can kind of see that it would fall out a little bit intuitively from this product definition. And then finally, phi of an element raised to the n, again, this meaning n-fold product of g with the group operation, is phi of g to the n. And we can kind of see that from the third bullet point. If we set all the gi's in this particular phenomenon to be the same and equal to g, then we get exactly this thing that we want right over here, or this thing that we want right over here. Okay, so there are some useful properties for the arithmetic of homomorphisms. So now I want to move on to some important subgroups that will play a huge role as we continue that come from looking at homomorphisms. Okay, so one thing that is discussed in a course like linear algebra is the idea of an isomorphism. And an isomorphism is a function that's one-to-one and onto. I want to remind ourselves of what these things mean. So onto means that everything in the target is hit by something in the domain space. Meaning, for every possible element, little g prime and g prime, there is a g and g such that phi takes g and outputs g prime. So no matter what you have in here, something in here is going to map to it. Onto means you cover the entire output space. Now, one-to-one means that you can't have two different outputs mapping to the same input. So I'll word that as if x and y are different, then phi of x and phi of y have to be different. Now, practically, this is not a very useful way in general to actually prove things are one-to-one. Usually, it is easier to use the contrapositive, and that is that if phi of x and phi of y are the same, meaning the outputs are the same, then the inputs must have been the same to begin with. Okay, so another way to think about this is there's a nice pairing between g and g prime. They map one to one, right? But then you also hit everything in g prime. So there's a nice pairing between g and g prime itself. And we usually write an isomorphism like this. We say the two groups are isomorphic. Now, one thing you learn in a linear algebra course is a way to test isomorphism by looking at particular subspaces corresponding to vector spaces. And the same kind of thing is going to end up happening with groups. So one particular thing to look at is what's called the kernel of this homomorphism, which is all the things that get sent to the identity element. So this is the set G in the group G, such that phi of G is the identity in the group on the right, E sub G prime. And this is usually referred to as the kernel. In linear algebra, you might talk about this as a null space as well. We don't really usually use that in group theory and just call this the kernel. And the image is the set of things in the output space that you get in general. So how do you talk about these? Well, you can talk about them as the outputs of all the things in G. So the things that look like 5G for some G in our group G itself. And this is the image of phi. So the big proposition is that both of these things are subgroups of the corresponding things that they lie in. So kernel of phi is a set of things in G that get mapped to the identity. So kernel of phi lives inside of G itself. Whereas image of phi is a set of outputs of G prime. It's a set of things that lie over here. The outputs in G prime. So the claim here is that they're subgroups. Kernel of phi and image of phi are subgroups of G and G prime, respectively. So we'll give a proof of this using the subgroup test. The subgroup test allows us to prove something as a subgroup in one fell swoop. This is notation here, this less than or equal to is notation for subgroup. We only briefly used it before, so it's a good idea for us to remind ourselves what that is. Okay, so there are two things we need to establish for something to be a subgroup. First of all, that it's not empty, there's something in it. And secondly, that it satisfies the subgroup test. So the kernel of phi is non-empty because we actually know something that is in the kernel of phi from our last page. The kernel of phi is a set of elements that get mapped to the identity. And we argued that the identity in G gets mapped to the identity in G prime under any homomorphism. So the kernel of phi is non-empty since phi of E of G is E of G prime. So E of G is an element of the kernel of phi. Okay, so now let's use the subgroup test. Now suppose x and y are in the kernel of phi. That means that both 5x and 5y are the identity in G prime. Then let's look at what happens when we apply xy inverse. According to how homomorphisms work, this is 5x phi of y inverse. And a thing for us to notice here is really implicitly there's a star here. That's the operation, but typically we just leave the operation out because it's implicit what it is. And then we argued that this is phi of x times phi of y all inverse, because the inverse of 5y is 5y inverse, something we proved on the first page as well. Okay, now since these are both in the kernel of phi of x and phi of y were both the identity in the group G prime to begin with, and so we end up with the identity in G prime. So xy inverse actually is in the kernel of phi. So by the subgroup test, the kernel of phi is a subgroup of G. Okay, cool. I think this is a great example of actually using the subgroup test. So this is a good thing to take a look at and review. It's sort of combining the stuff that we did with homomorphisms together with the subgroup test. Okay, so let's do a similar thing to prove that the image of phi is a subgroup of G prime. So first of all, we need to know it's non-empty. Okay, so the identity of G prime is in the image of phi because it's the output of something. Phi of something equals E of G prime. That something is E of G. So because phi of, or E of G prime, the identity in G prime is the output of something, it is an element in the image of phi. So this thing is non-empty. Okay, so now let's use the subgroup test again. Now suppose x and y are in the image of phi. Our goal is to prove xy inverse is actually in the image of phi as well. The thing is, the way we have x and y written here, they're not really amenable to use because we don't really have a way of we haven't taken the liberty of writing them in a useful way to recognize they are part of the image of phi. So to do that, let's actually make it explicit. Since they're in the image of phi, they're the output of something. So then x is phi of something, and y is phi of something else. So for some values, g and h and g. So our hope is that the value xy inverse is also in the image of phi. So let's play around with it. You have x, which is phi of g, and then y, which is phi of h inverse. And your hope is that this is phi of something in order to establish that xy inverse is phi of something, meaning xy inverse is actually in the image of phi. Okay, so we can kind of do what we did before a little bit backwards. This is phi of g, phi of h inverse, and then using the multiplicativity, this is phi of g h inverse. Great. And that is explicitly in the image of phi. So xy inverse is in the image of phi. So by the subgroup test, the image of phi is a subgroup of G prime. Okay, so these proofs were kind of abstract, but I think they're actually really quite useful in getting a grasp of how homomorphisms work, but also in understanding how to actually employ the subgroup test. Remembering you need to check non-emptiness, but then also using the terms xy inverse to establish these things. Okay, so now, just like in linear algebra, we'll be able to say something about whether or not we have a isomorphism between two groups by using the kernel and the image. So suppose we have a homomorphism between two different groups G and G prime. In order to test for being an isomorphism, you would need to be onto and one-to-one. That's part of what it means to be an isomorphism. We can use the two subgroups, image and kernel, to actually test for this. So phi is going to be onto if and only if the image of phi is all of G prime. And it'll turn out phi is 1-to-1 if and only if the kernel of phi is only the identity element of G. So that means that the only thing that gets mapped to the identity element of G prime is the identity element of G itself. Now, part of this proof is short and part of it is long. And the short part is number 1. Let's think about why. What does it mean to be onto? Onto means that everything in the target space, G prime, is actually the output of something from G. That's the same thing as saying that the image of phi is G prime, because the image of prime is all of the outputs of phi. So since the image of phi is all of the outputs of G when we apply phi, then phi is onto if and only if the image of phi is G prime itself. I want to think about this in terms of a picture to really get a picture of what's going on. So here you have G, which has a bunch of elements in it, and here you have G prime. Phi is a function that takes points from G to G prime itself. Now the thing is, it's possible that phi doesn't take your picture from G and map to all of G prime. It could be, in general, that phi only maps to a little piece here, which is called the image of phi. But if it's the case that the image of phi and G prime are the same, then you've hit everything in G prime, and so you are onto. So that's sort of the idea behind that piece. Now the second piece is going to be a little bit more interesting. The second piece says that if you have a picture, again, with G and G prime, with phi doing whatever it does, taking points in G to G prime, and it happens to be the case that if you pick this special element E of G prime, that the only thing that maps to it is G and nothing else, everything evades hitting G prime, thus somehow this tells us that this homomorphism is 1-to-1. This is not clear whatsoever why this ought to be the case. So let's actually get a sense for why it could be the case. Now, one of the things we have to remember here, and I'm going to write this in gray on the side, is that the way to check that phi is 1-to-1, again, is to check that if you have two things that map to the same thing, if 5x is 5y, then x is y. So to start, what we're going to do is actually look at an equivalent way of talking about the equality of 5x and 5y. That might be to an advantage to us for proving that phi is 1-to-1 if and only if the kernel of phi is only this one element E of G. Okay, so let's do that. So if x and y are in G, then 5x equals 5y if and only if we can multiply by phi of y inverse on the right, say this is only if f of 5x 5y inverse equals phi of x phi of y inverse. The reason we can write in if and only if is we can multiply in both directions. If we have this, we can multiply by 5y inverse here to get this. To go in this direction, we can multiply by the inverse of this thing on the right to undo the multiplication. So one of the advantages of having groups is that everything has inverses, so we can undo a multiplication of any sort. Okay, and this should be actually phi of y, 5y inverse. Okay, but these two are actually inverses of each other. So this happens if and only if phi of x phi of y inverse is equal to the identity in G prime. And using the fact that phi is a homomorphism, this is the same as saying phi of xy inverse is the identity of G prime. Okay, but this is saying that this element maps to the identity of G prime, which is the same as saying that xy inverse is in the kernel of phi. So, all in all, we're able to change this condition of 5x equaling 5y to be the same as a statement of this particular element xy inverse being in the kernel of phi. So now if we actually want to show that phi is 1-to-1, we can do something a little bit different. We can say, so to prove phi is 1-to-1, if and only if the kernel of phi is the identity, that is the thing that we were trying to prove to begin with, we can prove that the condition xy in the kernel of phi implies x equals y happens if and only if the kernel of phi is the identity in G. Okay, this is a complicated statement, so let's break this down a little bit. This entire thing here, xy inverse is in kernel of phi implies x equals y, that entire thing is the same as saying that phi is 1-to-1. The reason is that this piece here is the same as saying that phi of x is 5y. So you can interpret this, and I'll write it in gray, as being equivalent to 5x equaling 5y. Right, and so this is saying phi is 1-to-1. And we're trying to prove that happens if and only if the kernel of phi is E of G. Okay, so we have a few too many symbols here, which is a little bit unfortunate, but I want to encapsulate again the fact that this entire thing here is saying phi is 1-to-1 in a language that's using homomorphisms. Okay, so let's go ahead and actually try to prove these two implications. So the first implication we'll prove is the backward one. Okay, so here we're allowed to assume that the kernel of phi is E of G, and then we want to prove this thing. Okay, so suppose x y inverse is in the kernel of phi. Now in this direction, kernel of phi is the identity. So since the kernel of phi is E of G, this means xy inverse is E of G, which implies x equals y. You can multiply by y inverse on each side to get that this implies x equals y. And that's exactly what we wanted to show on this left-hand side, that if x, y inverse is in the kernel of phi, then x equals y. Great. So the forward direction is something that I want you to try on your own. So actually give this an honest try. Right? And the hint is to set y to be the identity in G and see what happens. So this proof is a little bit complicated and a little convoluted, but one of the things that's going to help us do is get a quick check for when phi is 1 to 1. Which is going to be very helpful for us when we try to establish when two groups that potentially look the same actually do look the same. Okay, so let's look at some examples to see things like isomorphisms or establish that groups are subgroups of other groups where we couldn't see so before. So the first example I want to look at is this example here, where we have a homomorphism phi from the reals under addition to the positive reals under multiplication. And we talked about this homomorphism actually in a previous class. This homomorphism takes a number and raises it to e to that number. And we had a sense that this might actually be an isomorphism, like a nice pairing between real numbers under addition and positive real numbers under multiplication. And the idea was that when you add two real numbers, it feels like the same thing as multiplying when you exponentiate them. Okay, so let's actually go ahead and compute the different parts to see whether or not that's the case. So the kernel of phi, again, is the set of elements in the domain space, so it's in the reals, so that phi of that element is the identity in the group on the right. The identity in the group on the right is 1, is positive reals under multiplication. So this is the set of real numbers so that e to that real number is 1. Now, by other types of mathematics, we know that the only way you can get 1 when you exponentiate an element is 0. And this here is the identity in the group on the left. So the kernel of phi is identity, and so phi is 1 to 1. This is an example of establishing that phi is a 1 to 1 thing. Okay, now let's look at the image of phi. I claim the image of phi is all the stuff on the right. No matter what number you pick on the right, there's something you can input to get that as an output. So why? Well, let's pick something on the right. Let S be an element of R positive. Then we need to think about an element on the left whose output is going to be S. And we had a suggestion of how to do this last class, actually. Our idea was to get S as the exponential of something, you can take the natural logarithm of that s. So phi of the natural logarithm of s, which you can actually compute because s is a positive real number, is going to work out to be s. This number ln of s actually is in our domain space. So since s was arbitrary, we were able to find a number that maps to it. We get that the image of phi is all the positive reals. So if we let s be a random positive real number, then phi of ln of s is s. Since s was arbitrary, phi is on 2. Great. So phi is an isomorphism. These two groups are actually acting exactly the same. The reals, under addition, and the positive reals under multiplication. And we're seeing how the matchup works. You have numbers like 2, -3, and 5. They get mapped to e squared, e to the -3, and e to the 5 respectively. And we can reverse this process by applying the logarithm to the thing on the right. And anytime we add two things here, it's like multiplying the two things here. When we add these, we get 2. When we multiply these, we get this. Okay, let's look at another example of homomorphisms and what they can tell us about things. So here we have a homomorphism we talked about earlier as well. 2x2 invertible matrices with real entries, mapping to the non-zero reals, and this is under multiplication, where phi of an element is the determinant. Okay, so the first question is phi is onto. It is whether or not phi is onto. So in our minds, what we think is you pick a random real number that's non-zero. Is there a matrix, and in this case, we're looking at 2x2 matrices, whose determinant is this particular real number, R? Well, there are lots of choices for what you can pick for that matrix, and I'll just pick one. So we'll let A be the matrix R001. Then det A, the determinant of A, is R. It's the product of the diagonal entries. So phi of A is R. This is true for any R in the non-zero reals. So phi is actually onto. Okay, let's look at the kernel of phi. The kernel of phi is the set of matrices A. It's a set of things in our domain group, such that phi of A is the identity on the right. It's under multiplication, so the identity here is 1. Phi of A is the determinant of A, so it's the matrices whose determinants are 1. We actually gave a name to this. This subgroup is called SL, and we'll put 2 in there for 2x2 matrices. SL2R, these are the invertible 2x2 matrices with determinant 1. So this contains a lot of things. It contains matrices like 2, 0, 0, 1/2, or 5, 3, 2, 5, 3, 3, 2. This has determinant 1, or negative 1, 0, 0, negative 1, etc. But we notice that as a consequence, because there's many options of things in kernel of phi, phi is not a one-to-one homomorphism. So the positive reals and the under multiplication and the 2x2 invertible matrices are not isomorphic. But there's something more interesting that's popping out of this. Before, to prove that this was a subgroup, we had to actually use something like a subgroup test. But now we don't. As soon as we establish that some set is the kernel of a homomorphism, it's automatically going to be a subgroup. So SL2R, the determinant 1 matrices, are automatically a subgroup of our original space of 2x2 matrices. It's kind of a cool finding. Also, it kind of makes sense that we should expect non-identity elements in the kernel of this. You would think if two groups are isomorphic, then if one is abelian, the other one is. 2x2 matrices under multiplication are not abelian, but real numbers under multiplication are the commute. So this is something that we could expect. But I want to emphasize this idea of how knowing that something is the kernel of a homomorphism gives you that as a subgroup. And it shows you a way to handle a previous assignment problem in a much quicker way using these foundations with homomorphisms. So we're going to look at a homomorphism from the symmetric group Sn on elements to the non-zero reals under multiplication. And this homomorphism, which will now give an abbreviation, SGN, it stands for signum, or in abbreviated terms, sign, and we're going to use sign very often. The sign of a permutation is this thing we actually talked about last class, where it's 1 if sigma is an even permutation. An even permutation means that it can be written as a product of an even number of transpositions. And it's -1 if sigma is an odd permutation, meaning that sigma can be written as a product of an odd number of transpositions. So last class, we proved that phi is actually a homomorphism. So today, as a consequence, the kernel of phi is a subgroup of Sn. Okay, but what is the kernel of phi? So the real numbers, non-zero real numbers under multiplication, the identity element is the number 1. 1 times anything is that number back. So the kernel, we'll actually write this explicitly, the kernel of phi is the set of permutations sigma in Sn, so that phi of sigma is 1. Now, the things that get mapped to 1 are the even permutations. So this is the set sigma in Sn such that sigma is an even permutation. And we had a name for the even permutations inside Sn. This was An. So here is a nice, relatively short proof of the fact that An is a subgroup of Sn by recognizing that An is actually the kernel of a homomorphism. In your previous assignment, you have to go through a long, laborious proof of this fact, but now you have a nice, short argument that doesn't involve as much work. This is interesting, and we're going to see more of this type of application of homomorphisms as we go on throughout the course. Great, so that's the end of the lecture for today. And so next class, we're going to talk about a particular class of groups and possibly use this homomorphism stuff to help us understand those classes more.